at what is called Euler's method, and then also our logistic equations. And so what we're doing is that we are using the concept of our dy over dx is about equal to delta y over delta x, as long as our delta x is small, right? And so if that is the case, if we use that concept there, then multiply both sides by delta x, and then what we have is our delta y, which is going to be increments that we have to search for, is about equal to our derivative, dy over dx, times delta x. So that's just kind of the general idea of what we're looking at. And so Euler's method is a way for us to find an approximate answer to a differential equation. Okay, so that's what we're going to be using. So we're using differentials to approximate a y-coordinate of a point to have a desired x-coordinate. And so we always need to have some sort of initial point that we'll be working with and an initial slope. And then we will be given our increments of delta x. So whether we say like over 4 iterations equally spaced or delta x is 0.5, that is what we are searching for. So essentially, just kind of in general, what we're looking at is we'll have, some sort of initial point, and we're trying to maybe evaluate a slope over here. So like if this was at, say, 2, and we want to know what would be the slope of this function at 3 without knowing what the function is. So without knowing the function, we can't like graph, take a derivative, plug in points, that sort of thing. And maybe it's a dy dx we can't necessarily solve, or something along those lines. So what we're going to be doing is we're going to be looking and just kind of walking our way over to that point. So given some sort of delta x, then we'll calculate our delta y, given that new delta x, that new delta y, and so on, and then just work our way over to that point. And so we're just kind of walking along, this imaginary function that we don't have or don't want to solve. Okay, so let's take a look at this first problem here. So we have let y equal f of x be some sort of solution to the differential equation dy over dx equals 2x. So now I am starting with a slope that we could easily solve and create a function and certainly get our slope value exactly instead of approximately. But it's just to give us like an easy one to start with, and then we'll move on from there. Okay, so yes, we can integrate this. Yes, we can substitute in this given condition of 1, 1, but we're going to pretend that we can't solve it, and we're going to use it to approximate. Okay, so our first step is we're going to start, this is our initial point here. And so we'll always be given some sort of initial condition to work with. And so that initial point is where we will start right here. So I have when x is 1, my y value is 1. And so that is what we're starting with, and we're starting at x equals 1, which was given, and we're going to use delta x to equal 0.1. So that means we are going to add delta x to find our next x value that we're going to move to. So I'm going to add 0.1. And I'm going to keep going because we're going to be trying to approximate 1.5. We're trying to figure out what is that y value. What is that y value at 1.5? And we know we're going up to 0.1. So I'm going to keep adding delta x each time until I get to that 1.5 value. So now what we need to figure out is, okay, now what do I add to the y value? So what is going to be that delta y? So now that is where Euler's method comes into play, is knowing, okay, what do we add to delta y? So again, this is our formula that we're using for Euler's method. And that's based on the fact that our slope, our tangent line slope is about equal to our secant line slope as long as delta x remains small, right? So close to that. So then this is our formula. So delta y is about equal to dy over dx times delta x. So now we're going to do a substitution. So I have dy over dx, which will always be given to us, which is 2x. And then I'm going to multiply that by my delta x, which was 0.1. And then that will find me my delta y. So let's go ahead and do that. So then delta y is going to be equal to 2 times x. And so x is equal to 1. And then multiplied by 0.1. So I'm just replacing the x value here. And so when I do 2 times 1 times 0.1, that will give me 0.2. And so that is my delta y. So now I need to add delta y to 1, so 1 plus 0.2, so then that would be 1.2. And so delta y is not going to stay the same because, your slopes are not going to stay, unless we had something, a function that was linear. Not a derivative that's linear, but a function that's linear. So if our slope was constant, then it would stay the same. So our delta y is going to change. So we're not going to add 0.2 again. We have to find our new delta y. So our new delta y is going to be our 2. So I'm looking at this formula again, and then times x. So my value for x is 1.1 now. And then times our delta x, which was 0.1, right? So every single time, this is the value that's going to change, and it's going to change according to whatever the new x is. And so then now let's go ahead and multiply that. So we have 2 times 1.1, which is 2.2, and then times 0.1, so then that would be 0. And then 2. So there's my delta y. So I'm going to add that to the 1.2. So 1.2 plus 0.22, so that would be 1.42. And then I'm going to find the next delta y doing the same thing again. So 2 times my value for x, which is 1.2. So I'm always looking over here. And then times 0.1 using this formula up here. And then I'm going to multiply that together. So that will be 0.24. And that's my delta y that I'm now going to add to the 1.42. So 1.42 plus 0.24, so 1.66. And then keep going, right? So it'll be 2 and then times 1.3 times 0.1. And so that gives me 0.26. And then I'm going to add that. So that would be 1.92. And so keep going, right? So just repeating that process over and over. So 2 times that value for x times 0.1. So 2.8, so 0.28. And then add that to the 1.92, 2.20, yeah. And then now we're done. So we would say f of 1.5 is about equal to 2.2. And that is Euler's method, just scooching along. Okay. So let's go ahead and take a look at another problem. So if I have this one here, so I know that my derivative, so dy over dx is x plus y. So this would be an integral that we would not be able to solve. We don't have the skill set. And then our initial condition is f of 1 equals 2. So let's go ahead and set up our chart. So my x is 1 when my y is 2. We're starting at x equals 1, and we have a delta x of 0.5. And I want to go until I get to 2. So I'm going to add 0.5 every time. So that would be 1.5, and then plus another 0.5, which is 2, which is where I'm headed to. So then how am I going to find my delta y? So delta y is going to be dy over dx, so that's x plus y. And then times delta x, which was 0.5. So then now to find delta y. So this is just that formula for Euler. So I'm going to do x plus y and then times 0.5. So that would be 3 times 1/2, so 1.5. So there's my delta y, and I'm going to add that to the 2. So 2 plus 1.5, that would put me at 3.5. And so now let's find my next delta y. So it's going to be x plus y. So my x is 1.5. The y I just found, which was 3.5. And then I'm going to multiply that by 0.5. So that would be 5 times 1/2, so 2.5. And so there's my new delta y, and I'm going to add that to the 3.5. So 3.5 plus 2.5 would be 6. And so then f of 2 would be about equal to 6. Okay, so that is Euler's method, just working through some number crunching, right? That's kind of the main idea for that one. Okay, and then the last little piece, or not little piece, I guess, but the last portion for 9b with our differential equations is what we call logistical or logistic differential equations. Okay, all right, so many things grow exponentially, but they can't continue to do so indefinitely. So this has to go with, like, you guys have like J curve, F curves from, I think that's from APES, either APES or AP Bio, something like that. So after a while, things start off growing exponentially. So they start off growing exponentially, but then they begin to compete for resources, whether it's food, space, water, money, whatever. So the growth begins to taper off as it approaches some sort of carrying capacity of the system. And that carrying capacity will be some sort of horizontal asymptote mathematically. And so in that case, our growth rate is going to be not only proportional to its current value, but how far away the current value is from the carrying capacity. Okay. So what is that saying? So what is that component saying? What it is saying is that if there's, so let's look at this example here so to kind of explain that. So let's say we have a rumor that is spreading through a school of 2,000 students. So that means the rumor cannot reach more than 2,000 students, right? Like that is our carrying capacity. That is our maximum amount of students that will hear that rumor at our school site. And so the rate at which the rumor spreads is directly proportional to the students who have heard the rumor and to the students who have yet to hear the rumor. Okay. And then as the number of people hearing the rumor approaches 2,000. Okay. So this is what we would call our carrying capacity. Okay. So that is our carrying capacity. And this is language that we will see pop up in the questions. It is also sometimes called our limiting value because as the limit approaches infinity, it would approach that value of the limit. And then, of course, mathematically or graphically, it is also called our horizontal asymptote. Okay, so at y equals 1,000 here, so we're going to look at a specific example. So at y equals 1,000, so that would be right here. That means that there are 1,000 people who have heard the rumor, and there's 1,000 people who have not heard the rumor. Okay. And so that is what we are looking at, so like there is that proportion. So we have this exponential growth that is occurring. And then at some point it stops becoming growth and it tapers out. So instead of becoming increasing concave up, it's still increasing, but then switches to that concave down. And that point right there, so that is a point of inflection, right? So a point of inflection where there's that change in concavity. All right, so in general, so this is a more specific, let's get some values on here just so we can kind of see what we can expect to see. So we have that exponential growth hits that point of inflection and then it begins to taper off. And then we have our carrying capacity, which we will often refer to as just y equals L because it will be a limit. And this point of inflection is at the halfway mark of that limiting value. So it's halfway. And that is where we will be growing fastest, right? Because that's at the tip of that exponential growth, right? So we have it's increasing and concave up until it hits the point of inflection. So that's where it would be growing fastest, right? And then it's going to slow the growth. So still growing, but the growth will slow because we are now concave down after that. Okay. All right. So a couple things to take note of is that the rate of change, okay, and I'm just going to use P for population because we use that often. The rate of change is going to approach 0, is giving us the same information as y is approaching L. So specifically, like if I were to look at, so I'm not at the end of infinity, but if I were to be towards infinity, so if I can imagine this being towards infinity, this line right here is becoming more and more horizontal, right, as it approaches that horizontal asymptote. So as that horizontal line becomes, as that graph becomes more horizontal, then the slope, of course, is approaching 0. And that is happening at the same time that the actual function is approaching that horizontal asymptote. And then this is going to be key and help us solve these problems. Okay, so a couple of equations that we need to kind of play around with so these are our logistical growth equations that we'll be working with. And both of these are relevant, but this is the one that tends to show up a little bit more often. So we'll kind of keep that in mind. So where if we factor out the L, right? So if we factor out the L, then we get that. So our K's would be different if we factor out the L's. So K would be, some sort of constant. But these are both the same equation. It's just the K's would be different. Like this would have a factor of L in it, so this one would have, this K would have a factor in L in it, and this one would not. Okay, but this is the one that we tend to see the most often. But they're both good. Okay, so P is our population, L is our carrying constant, and K is just our coefficient, our constant. And then when P, the population, is close to the carrying capacity, right? Then, so when P and L are approaching each other, so that would be like way out here at infinity, they are basically equal to each other. So then that ratio would be close to 1. And then also that rate of change would be close to 0 because we would be, again, we would be leveling out, right? The graph would be leveling out and becoming more horizontal. That showed it dipping down, but it's not. All right. And then if P is small compared to the carrying constant L, then our ratio is close to 0, right? And so that would be down over here. Okay, so we can solve this differential equation. This is definitely in our wheelhouse. We definitely know how to solve this. So I'm only going to do maybe 2 steps. So I would multiply the dt over to the other side. And then I need to get my p's over. So then I would divide those p terms over. And I would get 1 dt. And then definitely know how to integrate this side. That would be t plus some constant. And then over here, I would have to do partial fractions, right? And then do it in an abstract fashion. So in our wheelhouse, we can solve that, but we're not going to. Instead, what we're going to say is, all right, I know that if this is our logistic equation form in terms of a derivative, then this is it in its antiderivative, okay? And so that is what we are just going to trust, is that the integral of that will give me this. Okay, and then we just need to know how to use those equations. We don't need to have them memorized. So how do we use them? And that's what we're going to work with on the examples here. So what do we need to know? So what do we need to know? We need to know that the population is growing fastest when we are at the point of inflection, and that is when we are at half of the carrying capacity. We also need to know that we find that carrying capacity by taking the limit to infinity, right? That finds me a horizontal asymptote, which is my carrying capacity. We also know that occurs when that rate of change is approaching 0, okay? So that is what we need to know, how to work with those equations, and then those kind of 3 ideas there. So let's take a look at a few examples. Okay, so for this first one, we're saying that the growth rate of a population of bears in a newly established wildlife preserve is modeled by the differential equation right here. So dp over dt is given as this, where t is measured in years, and we want to know what is the carrying capacity. What is the carrying capacity? So the carrying capacity meaning when will that logistic equation, right, approach that horizontal asymptote. So the basic shape, right, is that kind of S curve. So it looks like that. And there's my point of inflection. So when is that carrying capacity going to occur? So given that derivative, so when is that derivative going to approach 0? So that's all I need to do. So I want to know when will that carrying capacity exist, and that's going to happen when the derivative approaches 0. So then I'm just going to take that derivative, set it equal to 0, use my 0 product property. Oops, I got the decimal in the wrong place. So then divide by 0.08. So when the population is 0, okay, well, that doesn't make sense, right? That's going to be like back here. And then the other one, 100 minus p equaling 0. So that would occur at 100. So then my carrying capacity of the reserve would be 100, right? And so that would be 100 bears. Any more than that, they're dying off. All right, so let's see here. So what is the bear population when the population is growing fastest? So that, again, that occurs at the point of inflection, which is at the halfway mark, right? So this is the halfway mark of the carrying capacity. So that would be 1/2 of the 100 bears we just got, which would be 50 bears. Okay, so then now they want to know what is the rate of change of the population. So whenever we hear that word rate, so this is back from chapter 3, I believe, or chapter 2, maybe it was chapter 2. So rate meaning d over dt, right? Whenever we see that word rate. And then here, population, so dp over dt. And we want to know when is that growing fastest. So when is that growing fastest? So then we want to know what is dp over dt, so my rate of change, evaluated at, oops, that was supposed to be a 5, at 50, because when was it growing fastest? When we had 50 bears, And actually, let me write this notation appropriately. Being a little lazy there. So that would be at 50 bears, so that would be p equaling 50. And so I'm going to use this equation right here and then just replace p with 50. So that would be 0.008 and then p being 50 and then 100 minus 50. And so that would be, hold on, let me get my calculator. Well, that would be 50, 25, 100 divided by 8. So 20. So yeah, 20. Okay, so 20 bears and then per year, so in years. Okay, so let's take a look at the next example here. Okay, so the population of Alaska from 1900 to 2000 can be modeled by this equation. So instead of giving it as a derivative, we're giving it into that other form, right? So the dp over dt is one form, and then the integral version is right there, where p is the population in t years. I'm assuming that should say in t years, after 1900, with t equaling 0 corresponds to 1900. So what is the predicted population of Alaska in 2020? So in 2020, then that would be t is equal to 120 years because t is 0 at 1900. So then they're just asking us to evaluate the population at 120. So we would just take that equation and then we're going to substitute in 120. And then I'm not going to type that into the calculator. But you are welcome to do that. 0.516 times t, which was 120. And then the outcome of this, so in your calculator, would be some grandiose number, and then people. Okay, so then now they're asking us how fast is the population changing in 1920 and then again in 1999. So in 1920, so we'll do that. So that would be at t equals 20. Oops. And then in 1999, then that would be at t equals 99. So there's like a couple of different ways to approach this problem, but essentially what we're looking for is what is p prime of 20. So we could actually, take that derivative. We can also use our calculator at Desmos to figure out that derivative and then evaluate it into 20, right? So that would be just using that kind of technology component. And so that would be 1678.078 and then people per year. I'd pre-populated this. But essentially we're using, so like in our calculator, we have our inderiv feature, which means numerical derivative. And we would just put in our function, so that p of t, we would actually type this equation into our calculator, and then we would evaluate it at t equals 20. And then I'll make sure I pop that into our format as well. Okay, and then the other way that we can look at this, so I'm going to backtrack right here, is that because of this formatting here, we know, our L is some particular number, right? And so we know that this is my derivative equation. So I can put that in for L here. And then I have negative LKT. And so from here, I can solve for what is K equal to, right? Also some number. And then I can substitute that into there. So that could be like potentially another way for me is to just put it into that derivative format, but we can certainly use our technology to just have us do that. Or you can use Desmos as well, right? Okay, so then now we want to figure out, and then of course we would do the same thing again for t equals 99. All right, so part C. So when is Alaska growing the fastest, and what would the population be then? So when, meaning, what is our value for t? So we're looking for a value for t. And then what was the population? So it's going to grow fastest, right, at that halfway mark. And so at the carrying capacity, half of the carrying capacity, right? I'm going to put that in parentheses. Okay, so what was our L value? So this is our L value. And then how do I know that? So that's just going back to just knowing how to use that formula, right? So if I look here, so my L value is that numerator, okay? So not something we have to have memorized, just knowing the pieces of it. So then that population would be 1/2, and I scrolled too far to see that number, of 895,598. And that would be 447,799 people. So that's what the population. And so now the when component. So then now I'm going to take that same exact equation I just had, or was just using or referring back to. And then I'm going to equal it to the 447,799. And then solve this equation. Okay, so lots of different ways to solve this. So I'm just going to put this over one. And then I'm going to multiply both sides by the denominator. And so I'm going to go times denominator times denominator. So then I would get the 895